the second of our two lectures on linear regression, we'll be looking at some more advanced topics, how to calculate confidence intervals for any point along the curve, or prediction intervals for new observation, how to do model comparison, and we'll briefly mention a few other possibilities. We're going to use the Ricker curve example again, so we'll just do a brief overview of it that we discussed last time, where the Ricker model is y equals beta naught x e to the minus beta 1x, and we get this telltale curve where we have a hump and then it decreases over time. We discussed how to use NLS in R, so for the Ricker data, if we had recruits as our y data and spawning as our x data, we would say NLS recruits tilde b0 times spawning, which is our x data times e to the minus b1 times spawning, with some good initial values. Last time we discussed how to find those values. Once it converges, we can use our normal summary commands, get outputs, standard errors, all that sort of thing. And of course, we can then use for new data, here I wanted to draw a pretty curve between 0 and 2000, and I can use the predict command on the new data with our model output to get estimated values, which I can then just add using lines command. Okay, so that's brief. That was the outline of what we did last time, just a little reminder. This time we're going to be looking at some more advanced topics. So we're looking at calculating the standard error for y hat given x, confidence and prediction intervals. We're going to implement confidence and prediction intervals on the Ricker curve example. And then we'll talk a little bit about model comparison and some other possibilities. Most of the hard work is going to revolve this standard error for y hat given x. Once we do that, everything else isn't too bad. So before we get into confidence intervals and prediction intervals in nonlinear regression, let's just remind ourselves about confidence and prediction intervals in simple linear regression, because there's some really nice parallels here. So just as a reminder, in simple linear regression, we'd use confidence intervals for the expected value of y given x to measure how accurately we've described the line. So if we have enough data, we should be able to describe it well. If we don't have much data, it'll be a pretty noisy line, and lots of possible lines could fit in there. Prediction intervals, on the other hand, are used to describe what values of y we might expect to observe for a new data point at a given x, so x equals x star. So this has to incorporate both our uncertainty in the line as well as the natural variability in the data. Even if we knew our line perfectly, there's still the normal variation that we'd expect to see from one data point to another. We'd have a formula that looks like this for the standard error of y hat. So s of y hat is a function. It has the underlying variability s, so that's our best guess for the residual standard deviation. It has a square root 1 over n plus how far x star was from the average value of x, so our new observation. If you're far away from the mean, you don't get quite as accurate a prediction for the line as you do close to the mean, divided by sxx. If you have enough data, n is going to be really large. Sxx is going to be really large. So this whole term will be close to 0, and s of y hat will be close to 0 if you have a large enough sample size. What that says is we can basically get arbitrarily close to the true line as long as we can collect an infinite amount of data. The formula for a 1 minus alpha confidence interval for how well we've predicted the line, so the expected value of y given x, will be beta naught hat plus beta 1 hat times x star for whatever value x we might be interested in, plus or minus our t statistic times the standard error of y hat. The prediction interval is very, very similar. So for a new value x equals x star, we're still going to have our best guess. This is just y hat here, that's y hat there, plus or minus the same exact t statistic. But now we're going to have to incorporate the natural variability s squared plus the uncertainty in the line sy hat squared. These are both random statistics. They are independent of each other. So if you have the variance of A plus B, where A and B are independent, that's the same as saying variance of A plus B equals the variance of A plus the variance of B. So if we want the combination of these two bits of uncertainty, it'll just be s squared plus sy hat squared. And then we want it in the original scale, so we'll take the square root. Okay, so those formulae should look reasonably familiar, even if you haven't seen them for some time. If you wanted to implement these in R, you would simply use the predict command. So predict can get us y hat, but it can get us a lot more if we are using it in an LM function. Predict is a very interesting type of function. There's a number of similar functions in R, where predict actually looks at what sort of object you're giving it, and then it calls a subfunction. So if you use predict on an object of type LM, it's going to then call a subfunction called predict.lm. If you use predict on an object of type NLS, it's going to then look for the subfunction predict.nls. So if you have an object of type LM, and say you want to get the standard error of y hat, you simply say se.fit equals true. And if you want a prediction interval, you say interval equals prediction. So in this example, I've just created some simple xy data. X equals 1, 2, 3, 4, 6. Y equals 3, 5, 9, 13, 18. So I made y about 3 times x. And my simple regression model, LM y tilde x. I want to make a new prediction at x star equals 5. So I'm going to say predict. Here's my model output. It's type LM, so predict will look for the subfunction predict.lm. Here's the new observations I want to predict at. In this case, it's just the one value x star equals 5. I want the standard error of the fit, and I want a prediction interval. And so it's going to give me some output. This first bit, fit. Fit is y hat, so beta naught hat plus beta 1 hat times x star of 5. It will also give me the lower and upper limits for a prediction interval, since I asked for a prediction interval. It will give me se.fit, that's just the sy hat. And of course, degrees of freedom and residual variation, these things are less interesting to me at the moment than those. Unfortunately for us, in the nonlinear world, if you look at the help function for predict.nls, what you'll see is for se.fit and type, it'll mention that these methods have not yet been implemented. So we're going to have to work a little bit harder. Essentially, we're going to have to work hard to find se.fit. Those two, once we've got the standard error, really aren't too hard. So in nonlinear regression, just to state that again, we can't use these nice functions in predict that have been implemented for linear models. We have to do a little more work ourselves. Essentially, what we want to be able to do is calculate the standard error of the curve for any particular value of x. And in fact, what we're going to do is something a little bit different than that. We're going to actually figure out how to calculate the standard error for any function g of theta and any value x. So likely g of theta will simply be the nonlinear model we have, and we're just plugging it in at a different value of x to figure out how well we've estimated the curve at that particular value. But what we're going to talk about is the much more general question of any function of those parameters. And the reason we do that is it's just as easy to solve the question, so find the standard error for g, as it is for the specific one of the curve. So once we find out how to do this for any function g of theta, we'll then apply that solution to finding the standard error for the curve at a given value. Now, you might be saying, theta, where's theta come from? All I mean by theta is the vector of parameters. So this is, again, quite generic. So in the Ricker model, we had beta naught and beta 1. So in the Ricker model, theta is simply the row vector beta naught, beta 1. Y hat's pretty easy. And figuring out what we mean by G, if we're finding the expected number of recruits when x equals 1,000, then in this case, G of theta x simply equals beta naught x e to the minus beta 1 x. That's the function G. And then I plug in x equals 1,000 into that, so I get G of theta is 1,000 beta naught e to the minus 1,000 beta 1. Once we find the standard error, we can then calculate t-based confidence and prediction intervals. Okay, so we're going to get started on this. Some of the theories a little bit beyond the scope of this class. If this was a more advanced mathematical statistics class, or say a graduate level class on GLMs, we might get into this if it was a really advanced graduate level class. But for this class, we're really just going to look at kind of a sketch of these results. We need to know the estimated covariance matrix of theta hat. So covariance of theta hat equals sigma hat squared times the inverse of the Jacobian matrix. Now, we're not going to worry about the details of that. It's going to be based on partial derivatives of our model and the data we have. So you've possibly run into a Jacobian matrix before, but don't worry if you haven't. The reason we don't have to worry about this is in R we do have the covariance matrix nicely implemented, and we simply use V cov and then our model name. So if our model was called model 1, it'd be V cov model 1. And that'll give us the covariance matrix. So we're going to need this component, but R gives us that for free. We can then calculate the variance of G of theta hat. So this is what we're trying to find. The variance, or the estimated variance of G of theta hat, will be the row vector of partial derivatives dg d theta times the estimated covariance matrix of theta hat times the column vector of partial derivatives dg d theta. All of this evaluated at theta hat. So ideally we'd want to know dg d theta with the true values of theta, but of course we don't know the true values of theta, so we have to use our best guess. Okay. The easiest way to kind of work through that theory is to just work through an example. So in this case, G of theta x equals 1,000 beta naught e to the minus 1,000 beta 1. And we've got this formula for the variance of G of theta. Okay, so we need three pieces. Well, really just two. We need dg d theta, the transposition of dg d theta. Once we have dg d theta, we get the transposition. But we also need this covariance matrix. So this first piece, the covariance matrix, is easy. We just say cov.hat or any other name that you like, and we call it, and we use the vcov command. So cov.hat equals vcov parentheses model 1, and we've got that sorted. The estimated derivative dg d theta is just the row vector, the partial of g with respect to beta naught, and the partial of g with respect to beta 1. Now, in more of a mathematical statistics version, we would have the students actually calculate this component. In more of an applied class, this would be done for the students, and we'd start off at the second line. So if we take the partial of our function g with respect to beta naught, it's essentially everything else is a constant, and beta naught, the derivative of beta naught times a constant is just the constant. So this first term is 1,000 e to the negative 1,000 beta 1 hat. The second partial we're interested in is the derivative of g with respect to beta 1. Well, this is really just an e to the minus a constant times e to the constant times beta 1. And the derivative of that will be to pull the constant here in front, and everything else sticks around. So we'll get 1000 times negative 1000, so negative 1000 squared, beta naught hat, e to the negative 1000 beta 1 hat. Now, the reason we've got hats in here, the beta 1 hat, the beta naught hat, is because we're evaluating this vector at theta hat, so at our best guesses of beta naught hat and beta 1 hat, or our best guesses of beta naught and beta 1. So if we plug this in, just taking the model output that we had before, our best guesses for beta naught and beta 1, stick it into this vector, we get about 504 and about negative 250,000. Okay, so at this point, we know what dg d theta is. We know what the covariance matrix is. All we have to do is multiply these two pieces together. And to do that, we're going to need to do a little matrix, some matrix operations in R. However, before we get there, what we want to do is just get started by calculating y hat. So if we want to find y hat when x equals 1000, I've got my model output. I can extract beta 0 dot hat as using the coef function. I want the first coefficient, that's beta 0, and the second coefficient is beta 1. So I've got beta 0 dot hat and beta 1 dot hat. I'm interested in evaluating this at x equals 1000, so I just call that x star. So y hat equals beta 0 hat times x star times e to the negative beta 1 times x star. That's just our Ricker curve. So y hat is 251.07. Now often when we multiply things, particularly when we've extracted them from something like a model function, there's some label that comes along that's attached. In this case, in this formula, the first thing that R sees is beta 0 hat. Beta 0 hat has a label called B0. And R is just trying to help us out and guess what we might want as a label. But that's really meaningless in this case. But we do care about the 251.07. That's our best guess for the expected value of y when x equals 1000. Okay, so to find the standard error, we've got all the pieces of the puzzle. We've got dg d theta, and we've got the covariance matrix for theta hat. We just need to use a little bit of matrix multiplication in R. We need transposition. In R, transposition is T of whatever matrix you have. And we need matrix multiplication. And matrix multiplication is percent star percent. So if we want to find this S of y hat for the Ricker curve at x equals 1000, I've got my covariance matrix, which I've called cov.hat. I've got dg.d theta. Remember in the theory, I wanted dg d theta to be a row vector. In R, if you say x equals c parentheses 2 comma 3, that creates a column vector. So the way to get a row vector is to transpose a column vector. So I'm going to use the T command for transposition and then enter my vector. So this gives me x star times e to the minus beta 1 dot hat times x star equals negative beta 0 hat times x star squared e to the negative beta 1 dot hat times x star. This is the exact formula that we came up with before, except for instead of specifying the value 1000, I've kept it generic and called it x star, so that if I wanted to find sy hat at x equals, say, 738, I would just change x star to 738, and I would use the same command line over here. I get my dg d theta output. There's my 500 and negative 250,000. To get the variance then, so cov.hat was a preliminary, dg d theta was a preliminary, but the variance is something I'm really interested in. It's dg d theta, matrix multiply, covariance, matrix multiply, dg d theta transposed. If you forget to do the transposition right here, but everything else was the same, when you say var.at1000, you put in this matrix multiplication, you're going to get an error message about non-conformable arguments. That simply means that you've got your row and column vectors mixed up. Once we have the variance, which should be a matrix with one row and one column, which is essentially the same as a scalar, we can then get the standard error at 1000 by taking the square root of it. And let's just look at the arguments here. If we have, say, p parameters, in our case p was 2, dg.dθ is going to be a row vector of dimension 1 by p. The covariance matrix will be, for p parameters, will be a p by p matrix. So we have a 1 by p times a p by p, and then the transposition of the 1 by p will be a p by 1. 1 by p, p by p, p by 1 will get us a 1 by 1 matrix for the scalar. So our standard error is just the square root of that, and in this case it works out to be about 15.6. This same general setup can be used for any curve as long as you know what dg dθ is. If you have some functional form here, everything else, all of these other calculations are going to follow the same. Once we have that, our hard work is done, and we can calculate a confidence interval for the expected value of y given, say, x equals 1000. This looks exactly like the confidence interval that we had in simple linear regression. We had to work harder for s of y hat, but everything else is the same. Our best guess plus or minus the appropriate t-statistic times s of y hat. So for the Ricker curve at 1000, I had already calculated y hat plus column minus 1, comma 1 times, that's the same thing as plus or minus, times the appropriate t-statistic. I had 6 degrees of freedom, times my standard error, and it gives me a range of about 213 to 289. Okay, so what have I measured here? What is a confidence interval? Well, that's a confidence interval for the expected value of y. So the expected we're 95% confident that the expected value of y given x equals 1000 is somewhere between 213 and 289 million recruits. All we've measured here is how well we fit the curve. It doesn't tell us if the curve was the right curve to fit. There might be a better curve to describe this model, a better model to describe this data. If it was the right curve, if we had more data, we could estimate it better. It doesn't tell us how many recruits we get in an individual year for a given biomass X. It's simply how well we've estimated the average number. So if we want to find how many recruits we get in an individual year, say suppose next year we would have some given biomass, what might we expect? Well, then we need to move on to a prediction interval. So a prediction interval for a new observation at x star equals 1000 needs to incorporate the uncertainty in the curve, just like we did for the confidence interval, but it also needs to allow for the natural variability in the data. So in this case, the estimated variance for y at a new observation x star equals 1000 has a component for the natural variability, s squared, plus a component for the uncertainty in our curve, s of y hat squared. And so the prediction interval for the new observation, just like in simple regression, will be y hat times our appropriate t-statistic, square root of s squared plus s of y hat squared. So if we want to calculate a 95% prediction interval for the Ricker curve at x star equals 1000, we first need to extract s, and we can get this from our model output summary of model 1, $sigma. That's our best guess for sigma. So we'll call that'll be s, y hat plus or minus the t-statistic times the square root of s squared plus our standard error squared. And we get a range of 175 to 327. Okay, so what's our interpretation of this? We're 95% confident that a new observation with 1,000 tons of spawning stock, or 1 million tons if you like, would produce between 175 and 327 million recruits. Okay, that's all we need to say about standard errors, confidence intervals, and prediction intervals. If you can follow that, you can, and you're given dg d theta, you can do this for any curve. I want to talk a little bit, very briefly, about some extensions. So some functions are reasonably common, and they've been programmed in more detail using what are called self-start functions. So for example, there's a function called the Michaelis-Menten model, which has a function called SSMicMen, or SSMICMEN. In the Crawley R book, there's details of other functions that have self-starting, and we'll give a quick example of this. In some cases, you may want to do weighted nonlinear regression, just like you might want to do weighted regression sometimes. Well, there's a weights option in NLS. That's quite easy to implement. And the formula I've given you before can be easily adapted to allow for weights. You might have group data, so you might want to have the same general nonlinear model, but you're going to get different parameters for different groups. For example, you might be modeling data that's different for men versus women, but the same general model. In that case, you can use the function NLSList. Of course, you might also want to have mixed effects models or be able to model autocorrelation. There's a different function, NLME, for nonlinear mixed effects that you can use if you want to extend to that. So just like you can do mixed effects models in mixed effects linear models, you can do mixed effects nonlinear models. And finally, you can compare different models using AIC. So I'm not going to go into the details of all of these, but we'll just briefly go over a self-start function and AIC. So what we're going to do is we're going to take the same Ricker curve and fake Trevally data that we had before, but we're going to compare that Ricker curve with the Michaelis-Menten model. So the Michaelis-Menten model, there's a couple different ways to parameterize it, but we're going to use the parameterization y equals ax divided by b plus x. We can either implement the full model in NLS where we specify starting values, or we can use the self-start function. So our model will look like recruits tilde SSMicMen, our x data, and our two parameters. And if I implement that and I add the Michaelis-Menten curve on top of the Ricker curve to this fake Trevally data, what we see is the solid line is our Ricker curve, the dashed line is our Michaelis-Menten curve. And looking at that, you say actually both models fit that data set quite reasonably well. It's very interesting though if you want to take this back into the biology. The biology is fundamentally different. The Ricker curve says that you'll go up, you'll reach a peak, and then you'll start to crash. If you have too much spawning stock, you're going to be above carrying capacity, your population will crash, and you'll get actually very few recruits eventually. The Michaelis-Menten model is fundamentally different. It says that as the spawning stock increases, it'll eventually reach an asymptote. You'll get a certain number of recruits, and at some point you'll have essentially diminishing returns, that even if you increase the spawning stock, you won't get any more recruits. This would be relevant if you were to get to, say, ultimately get to carrying capacity, but you don't have that possibility of crashing your population. Now, if you're just interpolating and making predictions, both of these models are giving you pretty similar estimates over the range of the spawning stock that have been observed. But if you're trying to use this to really say something about the underlying biology, you'd really need to be able to say which model fits your data better. So we'll get to that. And of course, if you're going to try to extrapolate, which is dangerous at the best of times and especially dangerous in nonlinear regression, you can see that the extrapolation for the Ricker curve starts to really drop, while the Michaelis-Menten model would stay up around 280 or so. Okay, so let's just show some R code, and I'm just going to walk through it, and this will be the last thing we cover in nonlinear models. So We'll talk about AIC in a second, but let's just hold on to that. If we look at the two possible implementations of the Michaelis-Menten model, the first model, I'm using NLS, and I'm specifying the full model, recruit tilde A times spawning divided by B plus spawning. And I gave some reasonably intelligent starting values that don't crash. I can also use the NLS model using the self-starting function, where I just say recruits tilde SS Mike men spawning comma A comma B. These two models are absolutely identical, and the summary of model 2, no matter how I specify it, is going to be absolutely identical. You do have to be careful that you use the same parameterization if you want identical output. There's different ways you can parameterize the Michaelis-Menten model, and if you parameterize it in a different way, you'll get different results, obviously because it looks to R like a different model. Now I'm not so interested in the summary here. I've created the fitted lines. Remember, for the Ricker curve, I had a vector new spawn that went from 0 to 2000, and I wanted to draw a nice pretty curve. Well, I'm going to do the same thing for the Michaelis-Menten model. I'm going to predict from the Michaelis-Menten model, model 2, this on the same data set, and I'll draw lines, and this time it'll be a dashed line, line type equals 2. So that was, if we went back here, that's how I got that dashed line. I can also use AIC for model comparison, just like you can in other models. You just say AIC model 1 comma model 2. And in this case, what we see, which you kind of got by eye, there wasn't really a clear difference between the two models. You might say that at this data point here, the Michaelis-Menten model is definitely not doing as well as the Ricker model. But for other data points, they seem to do pretty similarly. And we see that in the AIC, that there is some preference for model 1 over model 2. Delta AIC is 2.66, or if you were calculating AIC weights, you'd say about 93% of the weight is in favor of model 1, 7% in favor of model 2. So not really a definitive result, but a definite preference towards the Ricker curve over the Michaelis-Menten model for this particular data set. Okay, that's all I want to say about nonlinear regression. If you have a decent understanding of the things we've talked about here, along with a decent understanding of mixed effects models, you can go and look up and see how to extend nonlinear models to nonlinear mixed effects models, and so on and so forth. This is sort of the basic underlying element of nonlinear regression that you want to understand.